Like I just guessed like how many minutes. I just kind of like. How do you do that? Seriously, spend 100 of those. I would.
Yeah.
Does it look bad on your transcript or something if you have a pass-fail on the...
Does it look bad for pass-fail?
Yeah, like does it matter at all? Because I'm taking like this poli-sci class and it's like so dumb, and I'm pretty sure I'll be able to use it. Because I'm not going to study for it. So is it worth it to just change it to pass-fail?
I don't think... I mean, if you're trying to say I'm an expert in poli-science because I took this class, and then you point at it and they're like, why did you take it pass-fail? Then yeah, it might hurt the credibility. But if you're like, I'm an expert engineer and like I did great in engineering classes, I don't think someone would be like, well, what about this one class that's not in your major? I don't think that would matter.
Like drops and stuff, like they don't see my transcript.
Only if you give them your transcript. Yeah. Yeah, that's yours to say whether or not someone has.
To give companies your transcript?
No, usually just your GPA, and even that is. Yeah, yeah, for pass-fail.
Well, at least what grade is pass? Like, what do you need like minimum grade to pass? Like pass.
I think it's a C, like C minus or something. I think you'd have to check like student code of conduct. Or there's usually like somewhere on our website of like UConn what is. Yeah, does a D count as a pass? It does? Okay, yeah, so maybe D as well. Yep. Anything above what?
60, I think.
A 60. Well, yeah, even if the school says like a 60 is passing, it's up to the class to decide what is really the school. All the school can say is that a D is exemplary of like barely understanding the material of a class. Like it's not that you understood 60% of the class or 60% of the work. It's that there was not enough evidence to show that you are an expert. That one's kind of pedantic, but there's no absolute scores. Like they're all all the scores are made up anyway. It's just like video game points. It's like you get a point, you get a point. Anyway, yeah. Cool. All right, we're here at the end of homework 3, and the goal is like come up with an equation of motion, and then we're going to create like a general solution that if we know its initial position and we know its initial velocity, what does the function look like? Like what are the things that change and what are the constants that we can plug in? So there, like if we want, we could plug in like all sorts of different solutions and look at different times and all that. So if we want an equation of motion, where do you start? What's the first thing to do for an equation of motion? Free body diagram. Let's do that. I'm going to write up there a kinetic diagram. So we want free body diagram, kinetic diagram. In this case, there's friction between the block and the slope. There's a spring. Gravity is acting down. Write that on there. So we have like some kind of gravity. What do you think? What is that free body diagram? And then also the kinetic diagram. Like what does this look like? No, that's okay. Yeah. I was just giving you that. Yeah, I mean, sometimes we're all at the end table, but yeah, like the only difference between like tension and spring is that spring stretches, whereas tension is like, oh yeah, yeah. That's what I would say.
I know. Although my mom was like, I think we can start with I would have it.
We're doing like an equation of motion, we're accounting for everything, whether it's moving up, moving down, or like stop, like still. Yeah.
I really think that's just fine for this. I don't, obviously now it's
Oh, you think it's
yeah, yeah, it's like, it's quite honest, I like, she's in, I thought, you know, it's like, hey, here,
That one's not.
wait, what? How did she?
But I'm assuming it's spring.
I messed up the.
Yeah.
You messed up something there, yeah.
Yeah, but at some point it's going to stretch all the way down and then bounce back up.
I just have so.
All right, so I'll start off with the stuff that everybody, at least everyone that I saw, agreed on. Gravity acts in the direction of gravity. Nobody, I didn't see anybody say like, no, we have to account for the fact that this is on a boat and it's rotating or anything. And then normal force was normal to our motion and where the plane is sitting. So far, so good. Then I started seeing differences in opinion. Where is spring force going? Like up the ramp? Yeah. Is it always pointing up the ramp? No.
This is just if it's moving in a positive direction.
If its motion is positive, then it's negative force. Motion. What do we think? What's like definition for a linear spring? What's Hooke's law?
Negative kx.
It's negative kx. So, or we can say that it's k, like delta x, like whether you want to say it's negative or positive. So if that delta x, so there's some force 0 when delta x is 0. If I increase delta x, that means it's stretching down. Now it's pulling backwards. So this is the way you can draw it however you want, but you got to keep your own bookkeeping along the way. So I like to draw things in the way of if things are positive. So if its position increases, where is the force pointing? So that would be up the ramp. So then now I can say Fs is a negative k delta x, or this is like delta x is moving down the ramp somehow like that. All right, force of friction. What are you doing for that one? Same direction? I saw half and half, both directions.
In Part B it says
Yeah, well, we're going to assume that there is friction, get an equation of motion, and then solve the special case where mu is 0. Yeah. But otherwise, yeah, for a 0 vector, it doesn't matter. Ooh, excuse me. It doesn't matter which way you point a 0 vector, it's all 0. But so let's say mu is not 0, it's like 0.1, some kind of dynamic friction. Where does it point? Up the ramp? Any issues with that? Is this only going to move down the ramp, the block? No, because it's on a spring, right? Like if it moves down, at some point it's going to bounce back. So there are going to be times where friction is pointing the opposite direction, and we can get to that next, but at least for this, the way that we drew free body diagram, if velocity is positive, friction's negative. And again, that's how I like to keep track of my forces, but I won't force you to. You can do it your way. What does our kinetic diagram look like? Where does acceleration go? MA.
If it's slowing down as it goes down the ramp, then is acceleration up the ramp?
Yeah, so at least like in general, acceleration, MA is always going to be a negative kx. Like if theta is 0, MA is always opposite wherever the force, opposite its position. The bigger the position, the more it stretches back, the more it accelerates back to 0. So what does it look like here? Do I need a free body diagram to draw a kinetic diagram? I need it for my equation of motion, but do I need it for, does it determine what my kinetic diagram is? No. It's only describing like what is my definition of acceleration. So what is my so it's things like what is my coordinate system? Where are the components of my acceleration pointing? Has nothing to do with like where the actual vectors are going. It's just what are the components and how am I going to split those up? So how many components of acceleration should I have? 2? It is moving on a slope, right? We have. Do I want to say that there's MAX, MAY, like that? Rotate? Slope it? Yeah. Maybe look at the A1 and A2 vectors instead. Okay.
How do you show that it's not always moving down?
That it's not always moving down. With your kinetic diagram, that one, it's we're just trying to calculate like what is A. So if A is negative, then the velocity is either decreasing or increasing in the negative direction. So take this and rotate it like that. Like same direction, at least like MAX is along the slope. How does that look? Do we know anything about MAY? Do we have any constraints on motion? It's equal to 0. like that. But we do have like two vector equations now, right? Because we're assuming that it's a point mass, it's moving up and down a slope. We said it can't move off the slope, so AY has to be 0. So we should end up with, let's write out the A1 stuff and A2. So what are those A1 and A2 equations? We don't have to worry about what our definitions for friction and springs are for now. If you want, you can plug them in, but for the most part, we just want to get which forces are acting in which direction. That's where we're at right now. So what are the A1 forces and the A2 forces?
Friction and spring, kind of a component of
Spring, and then something with gravity. Okay. Makes sense to me. Oh yeah, so A2, at least in that diagram. Okay. Yeah, I was wondering where you were. You can define it however you want. Oh wait, is that in the same direction as that FS? Like it's kind of like the dot product of this vector is So Newton's second law, sum of the forces is Ma. So Max is going to have that negative spring force, so negative Fs, at least the way that my free body diagram is drawn. If you're drawing it differently, and keep your own kind of track of it. So negative Fs, total component is right along that. A negative force of friction. What about gravity? I saw sine and cosine, mg sine theta, mg cosine theta. Because this, I know these are kind of hard to see. This is A2, that one's A1, this is theta. Is it mg cosine theta or mg sine theta? Sine theta? Sine? Positive or negative? Positive? Yeah, pulling it down the slope, right? So let's try that. Mg sine theta. So if theta is 0, sine of theta is 0, and it's a flat slope. So our mg component becomes 0. Seems good, right? A quick gut check of did we choose the right sine or cosine? Cool. And then 0 in normal to our motion is our normal force, that reaction force. And then the other mg cosine theta component. So remember with the balloon, we got one equation of motion and one sum of the forces gave us some function to determine how much tension there was in that balloon string. Same thing happens here. We have an equation of motion and some equation that tells us what normal force is. Just here it's nice because theta is constant, so n is always constant. Actually, what I want to do first, before we start doing that, so if our position is like x in the A1, so this would be, if I call this 0, and that's x, v is going to be one derivative of that, so it's x dot. And again, it's along that A1 direction. What is A? What is our acceleration? X double dot. Yep. Yeah, we're not dealing with like rotating reference frames or polar coordinate systems here. We have like just a Cartesian coordinate system on an angle. All right, so I need spring force in terms of x, because I'm trying to figure out what is my equation of motion to describe x dot, x double dot. So how do I describe delta x as x? Yeah. So for a spring force, a spring is always, the amount of force is always just a function of how much it's stretched. So how fast it moves doesn't affect the actual force of the spring. At least for linear springs. You can have a nonlinear spring with extra like x dot terms or something, but we don't. We're just dealing with an ordinary linear spring. The bigger the x, the bigger the force. If you have a spring, what does it look like? Is it like when you take a spring out of the system, does it shrink down to length of 0? No. What does it do? Yeah, it has like an x naught, like some kind of like x naught or L0, like something. There's some like unstretched length of the spring, and we can use that to describe like delta x is x minus unstretched length. Kind of like that. And that just gets like that delta x value into terms that we can actually use for our equation of motion. And then we can solve for that final value. So we're not doing like, this part's not the hard part, but it's the hard engineering intuition part. Like, how do you actually describe this in a way that's solvable? What is force of friction? What's the definition for friction? Like regular, this one's dynamic, so it's sliding friction. What is that force? Sorry? Mu times n, right? And we solved for n. Is it always pointing up the ramp? Opposite of motion. What type of motion? Opposite position, velocity, or acceleration? Velocity. So we need a function. If it's opposite the velocity, then we need x dot to be part of this equation somehow. But mu is constant, and we just figured out n is constant. So right now it's not a function of x dot. How do we add something to that so it doesn't change the force, but it does change its direction? What else can we put in there? What do you think? I just want to know what you think. I know what I would do. I'm boring. I would do the same thing. What do you think? How do you flip? If you have positive v or negative v, how do you get it to change directions? At a negative? Okay. How do you keep track of like negative for this but positive for that?
You're saying what we add something from n for?
Mm-hmm. Yeah, like we need something like time something, or maybe like f of something, like create a function that changes the sign of it somehow. Like we got to change that. All we have right now is a constant, but we need it to change directions based on velocity. That one's constant, yeah.
Force of friction is constant no matter like how fast.
Yep.
Okay, so how is the force of friction a function of velocity if it doesn't matter how fast you're going down the ramp or up the ramp?
So the magnitude of this friction is always going to be the same magnitude, but it's going to keep changing directions. Because if I'm moving down the ramp, it's a negative, and if I'm moving up the ramp, it's a positive. Yeah.
Could you the velocity or the stretch over the magnitude?
Ooh. All right.
Velocity would just be negative. It won't change the value because it's equal one. It could be positive and negative.
What do we think of that? What does that do to our force? Doesn't change the magnitude, right? Because we're taking, if I'm moving 3 meters per second, I'm taking 3 over 3, multiplying it by 1. But if I'm moving negative 3, now I'm taking negative 3 divided by 3, now I get a negative 1. Yeah, and if you're kind of like reading, it also says like SGN, SIG, the sign of, so SIGN, not SINE, the sign, at least for a computer, it takes like the very first bit to figure out is it a positive or negative number. But somehow figuring out like is x dot positive? If it's positive, push it up the slope. If it's negative, push it down the slope. Cool. Good. Good. AX is x double dot. So what are, take our definitions for spring force, for force of friction. What is the equation of motion? Like, what is our final equation here? So now we're just taking all that work that we did, plug it into one like thing to say, this is my equation of motion. So what is that final EOM? Catching up or trying to figure out how to do stuff? Okay. So we have like the circle around those MAX is like that force and that gravity force. Rewriting that equation with all of our like, functions of x and x dot and x double dot. So that's my equation of motion is described as that one would be this one is when x is 0 or at till 0. Start at How's that look? Any issues or seems like, I mean, we did a lot of the hard work to begin with to set ourselves up. So we're doing something right. I'm gonna take this M, move it over to the other side, just because that's how I roll. Also gets rid of some of those like mg terms, just turns them into like g, like actual acceleration terms. Cool. And we've got an equation of motion for this block on a slope, sliding up and down. And this is true no matter what, no matter where it starts, where it's going. This is just the equation of motion to describe all of its motion. All right, now we have an equation of motion. We're going to ignore friction and solve for what is the general solution for if we know x0 and we know x dot 0. So in part B, assume x. So we're saying we know what its initial position and its initial velocity is. So what is x of t? That's what we're trying to say. Whenever it says like solve the equation of motion, really it's asking for like what is that x? What is x? And if you have x, then you have v and you have a, but
Is that x at time 0 equals x naught plus v 0?
oh, that's an and sign. Do you want an ampersand? Ampersand instead? Like, so we have two initial conditions and one constant is 0, so we can ignore one of the forces. So the general process here is that this is an initial value problem. We'll look at like solve IVP is like the general like numerical one for the project, but we'll get there. Do you mind if I rearrange this equation? I'm going to do some quick algebra. It's not too scary, but is that okay? I know we did a lot of work to get to here, but I'm going to rearrange it. You have no choice. No. So now I've got all my x's and x dots on one side, everything else on the other side. Have you done differential equations? Have you seen something like this before? Something, maybe? It's still the equation of motion, yeah. I just rearranged it. Like equation of motion, if you're trying to solve it by hand as an ordinary differential equation, it makes sense to separate it out like this, where you have a homogeneous part and a particular forcing function. If you're doing it with a computer, it makes more sense to use that first one that we created, because the computer is always going to say, for a given amount of time, here's acceleration, so let me integrate that to get to the next velocity in the next position. But two different approaches, same solution, still get to the same part. How have you solved this before? Maybe. Again, dynamics is hard because it's asking you to like take all this stuff from other classes. Yeah. Oh, okay. Using like find like the polynomial. Okay, we can do that. But how do we find that polynomial? What do we start with? Just the left side? Yeah. Can I give a little bit of background of why that works? Is that okay? Or just jump into, throw some m squareds and things in there? Let's give some background, why this works. All right. I'm going to take my one big differential equation, which has like the standard, kind of the standard unforced response and the forced response, turn it into two sets of differential equations, xh and xp. Xh is called my homogeneous, xp is my particular response. So x double dot is still x double dot h plus x double dot of p. So now when I take those and plug them, it seems like I'm making the problem harder, but really I'm making it easier by creating two easier problems. So x double dot h plus x double dot p plus k over m, xh plus k over m, xp is all equal to that same I didn't change the problem, but I did add extra things that I'm trying to solve for. Since I have these like homogeneous and particular things, I can add and subtract them the way that I want to, since they're my functions. This first homogeneous is just solving for when thing adds up to 0. And that's it. That's all I wanted to do. I don't care about any of the forced response. The next one, my particular, that's where I take care of everything else. Good so far? Yeah, and let's write out like homogeneous in particular. So in the homogeneous, so getting to that like polynomial part where like, all right, I know I have an x double dot, I have an xh, so there's like some kind of something squared term. I'm not going to use m because we have m in our equation, so I'll use s. So s comes up with like Laplace transforms. I don't know why. I feel like it should be L's or something. I don't know. Maybe we use L for too much stuff. xh equals a e to the st. So all linear differential equations are always ae to the st. Like that's just, it's the only thing that you can add to itself with all those derivatives and end up with same function. X double dot h equals s squared ae to the st. So that homogeneous function becomes s squared ae to the st plus k over m ae to the st, and all that has to be 0. It would be a pretty boring solution if a is 0, because that just means that I chose a function that is 0. It's like, get a life, Professor Cooper. It's like, I do. It's differential equations, ha ha ha. And then s, same thing. It would be pretty boring if that was 0, because now just it's a constant value, but that's what we're trying to solve for next. So I can divide through by those. So s squared plus k over m equals 0. And I think that's what you were saying, like m squared plus k over m equals 0. It's just, I didn't want to use m. So now we have s equals plus or minus I root k over m. And if I have those e to the imaginary number things, then really I'm just dealing with like sines and cosines. So xh of t is some constant times cosine omega t, another constant times sine omega t, where omega is root k over m. And at least for now, that's all I can do for my homogeneous part, because the next step is plugging in like what are my initial values to figure out what A and B are. I'm just going to take this whole thing and say that it's all equal to like capital D, so I can save a little bit of writing over and over. So D is just some constant number. What can I take two derivatives of it? So in the same way that I did up there, like e to the st, I don't want it to be an e to the st function. I want it to be a constant. I want to take two derivatives and end up with a constant. So what function can I take two derivatives of and end up with a constant value? Quadratic? What do we think? Will quadratic work? Maybe. We can try it, same way that we tried with the homogeneous. You want to try quadratic first? Maybe? No. Don't all speak at once. It gets confusing when everyone's yelling different directions. I'm only one person, for God's sakes. We could try it. I'll say that it's A, B, and C, right? X particular double dot is going to be 2A. So now 2A plus K over M, AT squared plus BT plus C equals D, where D is like all that other stuff. Every like power of t, like t to the 0, t to the 1, t to the 2, it all has to add up and equal each other on both sides of the equation. So my t to the 0 terms are k over m c equals, oh wait, let's do it in order, right? My t to the 1 are k over m bt equals 0. What did we figure out from this? What is A? How do I get k over m at squared to be equal to 0? A is 0. What is B? Also 0. And then C, we know that one, right? C is like m over k times d. But yeah, like equal to k over mc is d. Cool. And this will work most of, like, you can try almost any polynomial, and you'll end up with the same thing. For the most part, if it's constant on one side, your particular solution has to be constant. If it's a function of time, if it's a linear function of time, it's got to be a linear function of time, just a different coefficient. So now I know x particular of t is is L0 plus mg over k cosine? No, sine theta. Sine theta. Cool. Oh no, we're out of time. All right, sorry. X of t is a cosine omega t plus b sine omega t plus my particular L0 mg over k sine theta. We have like most of what we need. The last step is plugging in what are those initial values. So at time 0, x is x0, which is a times cosine of 0, so 1, a, b times sine of 0, which is 0, and then plus that constant, L0 plus mg over k sine theta. So a, that first a constant is x0 minus L0 minus mg over k sine theta. I also know initial velocity to figure out what is that b term. So I figured out a constant, now I need b. When I take one derivative, that cosine is sine, sine becomes cosine. So I only have v0 is omega b, and then that constant stuff is gone. So now I know b is v0 over omega, and I finally get, woohoo, the last solution, that x0 minus L0 minus mg over k sine theta. And I know I'm speeding through it, not explaining anything, but just getting stuff up onto the board. So I'm just taking those constants, plugging it all into my initial, like, that was my xh, and this is my xp. So I still end up back to that same initial guess that I can split it into xh and xp. Cool. Thanks for bearing with me. Thanks for staying a couple minutes late. We'll get the time back another time. Well, we've gotten time back before. We've left early. It happens.